Okay, welcome to a video lesson describing our orbit and Kepler's laws problems. Question 15a looks like this. We have the moon and the earth and the sun, and the distances are given and the masses of the planets are given. So the formula we use to calculate the force due to gravity is this, where g is the universal gravitational constant, and well, it's written right here, universal gravitational constant. Oh, there's Carson. M and m are the masses of the two planets, and then r is the distance in between the two planets. So if we use the equation for force and relate that to F equals ma, we can get that acceleration is force divided by mass. So acceleration due to gravity is gravitational force divided by mass. And if we do something like divide this by mass, these two masses would cancel out, and we would end up with the equation off to the right. Okay, so this calculates either gravitational field or acceleration due to gravity. They're basically the same thing. This question asks for the ratio of gravitational field on Earth to that of the Sun. So we're going to plug in all the information for Earth, plug in all the information for the Sun, and it looks like this and like this. Fortunately for us, these will cancel and cancel and leave us with this. When we plug it all into the calculator correctly, we get this. The book's answer was 2.3, so they were doing the reciprocal. And the wording is a little tricky when they say the ratio of something to something. If it's Earth divided by Sun, you end up with this. If it were Sun divided by Earth, you'd end up with this. So because the wording was tricky, either is acceptable. If you're plugging this into the calculator and not getting this, you're not doing it correctly. So I recommend using parentheses, especially around the numbers in scientific notation and whatnot. Question 15b has a situation like this, where the moon, where the moon is over here, and Earth and Sun, and asks us to find the net gravitational field. So first of all, let's take a look at the units here, because the units for acceleration, it says accel, the units for acceleration are meters per second squared, which, given that a Newton is a kilogram meter per second squared, leads us into gravitational field being in units of Newton per kilogram. So this is like a force per mass. Okay, and if we look back up here, in essence what we're doing is g is a force per mass. Okay, acceleration due to gravity. So acceleration due to gravity or gravitational field, they're the same thing. In general, for a gravitational field, we would express the units like this, and for an acceleration or acceleration due to gravity, we would express the units like that. They are the same thing. Chelsea's in here to steal donuts.
No, I'm here to steal my goldfish.
Okay. So what the question asks is, what is the net gravitational field? The Sun is pulling on the Moon, the Earth is pulling on the Moon. This question would be relatively simple if they were pulling in the same direction, but they're not. So what we're going to do is plug in the values for the Sun to get this, and plug in the values for Earth to get this. So notice how the acceleration due to gravity on Earth, so if you were right here, let's draw you, this is not to scale, there you are on the surface of Earth, the acceleration due to gravity of the Earth is 9.8 meters per second squared. The Moon is so far away that the acceleration is some small fraction of that. Okay, so if you got these values, great. The reality is we would have to take this force and break it into components like this and like this. And so we would take the Earth's component and add it to the Sun's component, and then, we would get something that looks like, well, maybe you don't know because this is sort of new, but we'd get Earth and Moon, and Sun and Sun, and then the resultant force would actually be something like this. We're going to do more practice with forces in 2 dimensions like that. So for this question, if you ended up with these values, that's great. The thing that I'm confused about is if the gravitational field on the moon due to the sun is greater than that of the Earth, right? 0.005 is greater than 0.002. How come the Earth doesn't pull the moon away from us? Okay, next page, next question, 16, was, what's the acceleration due to gravity on the moon? So we know that it's less than 9.8. We see the astronauts sort of bouncing around. But using this formula, universal gravitational constant, mass of moon, radius of Earth, notice how I immediately turned that into meters, as I did in the previous question and forgot to mention it. So, whoops, sorry. But if a distance is given to you in kilometers, you may as well just turn it into meters because in physics we use the MKS system of units, meaning meters, kilograms, and seconds. So if this is not in meters, your answer is going to be wrong. That's the acceleration due to gravity on the moon, and it's about 1/6 that of Earth. 17, mass does not affect orbital period or speed. All right, so President Eisenhower's like, hey, the Russians launched a satellite. You better figure out how heavy that is. And the scientists were like, actually, Eisenhower, we can't, because if it weighed 100 kilograms or 1,000 kilograms, it would be tracking the exact same path at the exact same speed through orbit. And so given the instrumentation that we had, we couldn't figure that out. And we still couldn't. You could put a satellite, 2 identical looking satellites into orbit. I'll draw a little picture. 2 identical looking satellites into orbit, and they're orbiting right next to one another, yet this one inside has a big lead block. So this would have a much higher mass, and this would have a much lower mass, yet they would be orbiting at the exact same speed, and we wouldn't be able to tell that unless we had X-ray vision, which we don't. Question 18 shows or asks about 2 satellites. One is 160 kilometers, that's a km away, and the other is 150 kilometers away. So substituting into, well, first of all, you don't actually have to do this. It asks about the time to go around and the speed. And so we know, more students here to steal donuts. I'm almost done recording here. The closer the satellite is, the faster it goes and the less time it takes. So just by looking at it, oh great, you could know that A is going faster and will take less time, and B is going slower and will take more time. But I actually substituted in here, so this would be satellite A and this would be satellite B. And if we were to simplify, okay, I put these into meters, I simplified, I took the cube of it, and the period of orbit for A is 82% the period of orbit for B, meaning less. So this goes faster and so this takes less time. Then I actually went ahead and did a calculation using speed as distance per time, and it's going in a circular path, so it's 2 pi r all the way around, dividing by time, or the period of orbit, and ended up with this, indicating that yes, A is going faster than B. Okay, last page. Number 19, difference between theory and a law is sort of that law is something that's just observed all the time and isn't questioned, whereas a theory is something that is proposed and then backed up by experimentation. So Einstein talking about four-dimensional space-time being warped by gravity and that kind of thing has been backed up by experimental results. Gravity on Earth, as we know it, is so familiar to us, apples falling on our heads and whatnot, that we consider it a law. Question 20, here you are floating around in outer space and you kick the chair. Ouch. It would hurt because even though the chair is weightless, it still has mass. 21, here's a top view of Earth, and so we know that the sun rises in the east, so it means that the Earth is rotating this way because the east sees the sun before we do on the west coast. So if you launch the satellite this way, it would have an initial velocity of almost 1,000 miles an hour going around the Earth. It has to go a lot faster, but this would use the Earth's rotation to actually get it going and be helpful.